This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
There's only so much mashing of the keyboard I can do. This is not good. The big question is, who do you call when your system doesn't turn on?
Can you use the cap one? And you have the iPad.
No, the trouble is I can't access any of the features, which means I can't get the projectors turned on. And so I can't get this to... It's not a good start. This is the bit where I have to hope you all have access to the slides. Wow. I've never seen anything like this. Well, there's an interesting test of my quality as a teacher, as to how well I can pull you through a lecture if I can't show anything on the screen. Oh, God. Do you know it's entirely possible I might have to use the whiteboard, which is like utterly forbidden these days, and wave my hands and talk to you rather than stare at my screen. So, just a quick announcement. Much to my embarrassment, the touch screen that activates the projectors is not responding, which means I can't turn on the slides and I can't turn on the overhead projector. So suddenly I become an old school teacher with a pen in my hand on the whiteboards, which is like utterly forbidden because it's not lecture captured. My voice is lecture captured, and I presume if I have something up on the screen it's lecture captured. You have the slides, but I'm going to have to wing it. I'm going to have to teach you the things I want to teach you today by drawing on the board and talking to you. I would like there to be an option, and I can't immediately find one. So I also hope that you guys have access to the slides through the LMS. Now would be a fantastic time, if you haven't already got them on your screen, to download them and have a look at them. Yeah, no, it looks like no matter how much I press the screen, nothing will happen. So you're stuck with me talking to you. Now, luckily, I've taught this a couple of times, and I'm pretty sure I can do a decent job by waving my hands at you before I go and yell at someone in IT to fix things. So, what are we doing today? Apart from recovering from embarrassment. Is that even readable? It is? All right, great. This is a good beginning. I've got things I can write on, and now I get to give you the preamble. Which means I can walk around the room because I'm not stuck to my desk. So, just to recap, we have built up all of our boundary conditions and language for the problem, for the thermodynamic analysis already. We've looked at system boundaries, outside the system, inside the system, different boundaries we can define. We've looked at the working fluid and its properties, and we've looked at processes on the working fluid. We've done it at a fairly introductory level, which is we've just introduced the words, and we haven't done a lot of the maths behind it. And then on Friday we started to look at ideal gas as one of the two categories of working fluids we'll play with. One category is ideal gases, and they have a relationship between their properties, which is referred to as the equation of state. And that was, for an ideal gas, that was the ideal gas law. So that was your PV equals nRT, or your P little v equals RT, or your PV equals M universal T, whichever version you want to use. That's nice, because if your problem says I'm an ideal gas, if your working fluid is I'm an ideal gas, then you don't have to look anything up. You just know you're hunting for, do I have two properties, and therefore I can use the ideal gas law to work out the rest of my properties at any particular state. For steam, or for not ideal gases, you have to look up the properties. So you still need two independent intensive properties to pin down your state, but to find out the other properties, you can't just plug them into an equation. You have to go looking it up. Now, we look them up in property tables. And so that's basically what today is about, is understanding that they exist, what property tables exist, how you're going to use them, when you would use them. This stuff comes early on in the subject, because if you get this wrong, you get the question wrong, right? So the division between where am I getting my properties and how do they interrelate is one of the fundamental splits and choices you'll make in your thermodynamic analysis. So it's kind of the first stop. You pick up the question and your brain's jumping into it going, where's my system? What's my working fluid? And is that working fluid ideal, or is it a vapor? Is it ideal gas or is it a vapor? Basically, which tool set am I taking off the shelf to solve this problem? If you use the wrong tool set, you get the wrong answer. Also, when you're just learning thermo, if you pick the wrong tool set, often you'll get significantly less marks than just the wrong answer, because your job was to choose the right tool set. It wasn't to get necessarily the right answer. So the things you get assessed on, particularly in thermo, is are you approaching the problem with the right thinking? So with the property tables and with steam, we're going to have a look at, in the first few slides, we're going to have a look at how complicated the steam properties are and why you would tabulate them. So I'll just cover over that relatively quickly. Then I'll go through, I was going to nicely show up on the board. Now I have to sketch the property tables, which is not fun. Luckily for you guys, you have them all in the resources tab of LMS. And there's a nice file there with as many property tables as you could use. And we'll learn how to walk our way around them. And then right at the end, we're going to learn a new concept, which is the concept of quality, which I've already alluded to. When we were looking at the boiling water exercise, we talked about how much of the water was boiled versus how much was not boiled yet. So what mass was vapor, what mass was liquid. There is a metric, and it's just a percentage. What percentage boiled of the mass is it? And so when you are during the boiling process or the condensing process, which is the opposite, you need to know the quality. You need to know the quality of the liquid, of the substance, the working fluid, to be able to pin down its properties. So that's today's lecture. If I choose a marker that's not readable, if you can't see what I'm doing, oh, that's a much better one. Let's get rid of this. Let's get a couple of colours. Then please let me know if you can't see stuff. But also, basically everything that I'm going to scribble down is in the slides, and so you may be able to see it easier, probably neater, if you have them in front of you. So that's the introduction. The most common working fluids we've got are air and water. I'm going to have the presentation in front of me because it makes it easier for me to keep track of what I'm doing. There are other working fluids like carbon dioxide, ammonia, hydrofluorocarbons. You don't see ammonia a lot. CO2 is a bit experimental in power cycles. Hydrofluorocarbons are used all the time in refrigeration. And those ones, anything that can turn from a liquid to a gas during the time that we use it, falls in the category of vapor fluids as opposed to an ideal gas. So, what I want to imagine now is on a property diagram, so two axes, must label them. There's no point me just scribbling down two axes. I have to tell you what it is that we're looking at. Let's have a look at pressure and volume. So this is now called, or specific volume, is now called a PV diagram. I want to trace the process of heating up some ice. So somewhere down here, let's say I've got ice at minus 20 degrees. Actually, no, let's do a TV diagram. It's easier. It's easier to imagine temperature. If I start down here at minus 20, I have a certain specific volume per unit mass, and as a solid, I've probably got one of the smallest specific volumes in the spectrum of the specific volumes I could have. So eventually, when I'm a gas, I'll have lots of volume per unit mass, probably about 1,000 times bigger than what I have as a solid. But on the way to becoming a solid, I have to go through being a liquid. I have to melt, and then I have to boil, and then I become a gas. So we're going to trace that path for water. And there's a few little kink points that come along. So let's have a look at what happens. I'm going to trace a line. Let's start here. Where is the first interesting temperature? As I start to warm this up, what's the first interesting temperature I hit?
0.
Okay. So let's heat up to 0. This won't be to scale. On my way up to 0 degrees, is my specific volume going to go up or down?
Up.
Why?
Because the liquid increases.
I'm not a liquid yet, I'm just a solid. So just a lump of ice.
Yes.
Have I changed? Is it going to change or not? If I heat up some steel, is it going to get bigger or smaller or stay the same? Generally, it won't be big. It won't be a huge change, but generally, as I warm things up, they'll get a little bit bigger. So I'm not going to go like that. I am going to get a bit bigger. And then here comes the game. Now I'm going to melt. And this is the weirdest thing about ice. My ice cube in my glass of water is floating or sinking? Floating. Which means it's more or less dense than the water. Less dense. All right? Which means its specific volume is more or less. Remember, specific volume is the inverse?
Yes.
So the has a smaller specific volume. So the ice, this is ice here. I now want to melt it, make it water. The water has a smaller specific volume. So actually I go this way until I'm all melted. Then I start to warm up my water. And for a while, this is the weirdest thing about... I can tell you that an ice cube floats on water. You know an ice cube floats on water, but to see it drawn is weird. Up to 4 degrees, that process keeps going. So, that's the least dense for a long time. So the most dense for a long time, which means my ice is going to float on that. So what's happened here is I've gone from 100% solid to 100% liquid. And then once I get past 4 degrees, I start to behave like a normal thing again, which is to say as I warm it up, it starts to occupy more volume. So my liquid, this is all in the graph, so you don't actually need to scribble it down. My liquid gets bigger and bigger. And then what's the next interesting thing that happens?
100.
I start to boil. So somewhere up here, while I am in the process of boiling, what is my temperature? Can it go above 100 while I'm boiling? No. So, the melting and the boiling process are constant temperature processes. They're also constant pressure processes. You don't see that on this graph, but I tell you. And then eventually I am 100% boiled, and then off I go. Whoosh. So that's not a neat equation. If I were to plot the relationship between temperature and volume, that's not a neat equation. If I were to try to find, if I knew my point here, I probably also don't have a neat equation that matches then to pressure. I've now got temperature, specific volume, that should give me my state. It does, in fact. 2 independent intensive properties gives me my state. but I still need to look up the values to find out what my internal energy, my enthalpy, my entropy, my pressure are. If I'm here, or if I'm here, if I'm here, if I'm here, what's my pressure?
Should be same.
Okay, this is a constant pressure line. And what is the pressure? How do you know?
Because
I didn't write it anywhere, but so how did you know?
you assume it will boil at 100.
So it's not even an assumption. If I've told you it is boiling at 100, that's actually a feature. It only boils at 100 at 1 atmosphere of pressure. So by saying that I'm boiling here and melting here, I've actually told you what the pressure is. If I told you these numbers were different, you could go and look up what is my pressure. If I told you that I am boiling at 95, will my pressure be higher or lower? Right, so as I go up the mountain, it's easier to boil. As I get to almost a vacuum, the water almost wants to boil by itself. As I put more pressure on it, it gets harder and harder to turn it into a vapor. And so at high pressures, it takes more energy, more temperature. So if I were to keep drawing this line at a lower pressure and a higher pressure, I would get a nest of lines. So if I were to draw at a higher pressure, I'd get a nest of lines here, and I'd get a different nest of lines here. Just make sure I scribble my lines nice and nicely. This comes all the way around here. This comes all the way around here and like this. If I were to draw a lower pressure one, I get a boiling line here, and I get this little groovy line here, and I come in here, and I get down here. And then these little breakpoints I can start to join up, and I get a groovy line that marks out at any temperature where would I start to boil, what specific volume would I start to boil, what specific volume would I be after I finish boiling. This is called the saturation line. So all these definitions are also in the slides. And there's a bunch of other lines or points. This guy up here, right at the top, imagine I'm at the pressure. So here's a temperature. And I'm at the pressure that takes me through this point. What happens with my boiling here? I'm a liquid coming up here, and I try to boil. What happens?
Everything boils at once.
Everything boils at once. Does it even boil? What happens if I was just above? What happens if I went this way and I tried to boil? All right, my world just broke. This is called supercritical up here. And what it means is I no longer have a definition of the difference between a liquid and a gas. There is no surface tension. There is no line that says, here's my liquid blob and here's my gaseous stuff. Everything is a uniform fluid that is more or less dense. So that here I can move around and change my specific volume, but I don't have a line that says here's a blob of liquid and here's a blob and here's a space of gas. So this point here is called the critical point. It's both a temperature and a pressure. A fluid, any fluid or any substance has a critical temperature and pressure. And it's a pair of numbers, and it's a property of the fluid, of the working fluid, of the working substance. So here we've got critical point. There. Inside here, I'm going to get some different colors so we can see. This is fun. I haven't written on a whiteboard for so long because we're basically not allowed to. Luckily, I'm not going to put anything on the whiteboard that isn't in the notes, so there's no one at home watching the lecture who's going to miss out. And my voice will match up with the slides. So this is all perfectly synchronized, but you guys get the benefit of me enjoying scribbling. So this here is called the saturated region. In here. In thermo, saturated is a code word for somewhere between fully liquid and fully gas. It's a code word for the process of boiling or the process of condensing. So this way is boiling, this way is condensing. Same process, just different direction, yes? Yep, noted, thank you. It's fun to draw with, but not useful. So, boiling, condensing. Okay, and saturated. So I'll get them back up. Does that work? Cool, good. There's a couple of other spots in here. Now, supercritical, in thermo, we tend not to work in the supercritical stage so much, particularly in the early days, because it's a bit of a weird space and it's usually pretty high temperatures and pressures. Over here, now there's a fuzzy line somewhere around here that sort of defines when you're getting away from supercritical and you're really just a gas again. Over here, once I'm away from the boiling process, is what's called superheat, superheated vapor or gas, or the superheat region. So, when I'm a gas, but I'm close to the saturated line, I still need to look my stuff up on the property tables. So I've shot out here, I've boiled my steam and I'm using it in my steam turbine. This region here, I'm still looking stuff up. If I get super hot and far away up on the specific volume or higher pressures, I then get into a superheated gas and I'm on a different set of tables. Eventually, I become an ideal gas if I get far enough away from this curve altogether. Usually we don't, when we're on a steam problem or a vapor problem, we usually don't get away from needing the tables, but we do switch from, and I'll introduce a set of tables called the superheated tables and a set of tables called the saturated tables. We have tables for here because it behaves funny, and we have tables for here because they behave under different rules. In here, if I tell you the temperature, I have told you the pressure. The pressure at which something boils defines the temperature at which it boils. The temperature at which something boils defines the pressure at which something boils, which means they're not independent. So during the boiling, telling you the temperature doesn't tell you the energy, doesn't tell you the state. I need one more piece of information. If I told you the specific volume, that's great, we've done it. If I told you something else that isn't pressure, that's great, we've done it. But I can't tell you the temperature and pressure here and pinpoint where I am on the boiling process. So we have a different set of tables here to do that, and a different set of tables up here. And we'll play with those. Liquid saturation, vapor saturation. Underneath here, if I drew up some dots, I'd end up with a solid liquid line. And somewhere in here, I'd also have this thing called a triple point. And the triple point's weird because it's the point at which you get, at the same point in time, you can have solid and vapor and liquid in the same vessel, in the same location. So much like the critical point, the triple point has a defined temperature and pressure, and it's a property of the substance. Generally, we don't play with solids because they're not easy to move through turbines and they're not easy to move around in piston cylinders. So generally in thermo, we're dealing with this, the process of liquids turning into gas and gases turning back into liquids. When we're liquids, we can pump them around and move them pretty easily. It doesn't take a lot of work to increase the pressure. When they're gases, we can put them through turbines without ripping the turbines to pieces by hitting them with little droplets. And we can transfer energy up and down these lines. So that's that's why the properties are weird of water, and it's why you need to write them down in tables. So let's have a look at that. That's a thought experiment done. The rest of those, the words of those definitions of the points that I've marked out here are in the slides. And I've mentioned now, does anyone have the tables on their device in front of them or near them? I'm not saying you need to, but if you happen to have them, that's great. It might make what I'm about to do much easier. What I'd like you to do, maybe not immediately, but this week, is make sure you've been into LMS download the file, the property tables file, and open it. I don't want you to do anything with it, just open it. Look, make sure your eyes have seen the document and you see what's in there. Because what we're about to do now is on a whiteboard, and then there's I've taken like snapshots into the slides because I've just taken the bit that I want to talk about. I want you to have seen the tables so that you see how big they are, how many there are, and imagine that you're solving problems with them, because you will. Over the next 4 weeks, we will be using these tables over and over and over again. So this week, I want you to have seen them. I want you to have downloaded and opened that document. Now, I've said we've got tables for here and we've got tables for here. So first we're going to talk about the saturated tables, then we'll talk about superheat tables, and I'm actually going to scribble up the headings of the tables, just so you can see them. At the top of the table, it will tell you what type of table it is. That's good. That's kind of normal behavior. But it means when you first go hunting for something, you need to know which table you're looking for. Sometimes you don't know. So let's get the headings up. If I'm writing on this board, is it still easy to see over there? I guess I'll start writing before you can answer the question. It would say saturated steam table. STEM, nice. Steam table. And so the keywords there, it would tell you it's a saturated table, not a superheated table. That's what you're looking for. It would tell you that I'm not an air table, I'm not a CO2 table, I'm not an ammonia table, I'm a steam table. You have two versions of this table. Version 1 is called the temperature table, and version 2 is called the pressure table. The content of these tables, the data contained in them, is completely self-consistent. It is the same information. You get two tables. This one's the temperature. This one's the pressure. You get two tables because sometimes in a problem you get told, I'm boiling at 100 degrees. Sometimes in a problem you get told, I am boiling at atmospheric pressure. This table has enough information that I could work out at atmospheric pressure what was the temperature I was boiling at. This table has enough information so that I could say at 100 degrees what pressure am I boiling at. But if you're handed some information on a platter, you might as well go to the table that makes your life easier. So in this one, let's do the pressure table because that's the one I've got in the notes. It has a couple of columns. It's got pressure, and then it will always tell you a symbol and a unit. The unit is important because some of the tables are presented in kilopascals, some of them in atmospheres, some of them in megapascals, some of them the temperature will be in Celsius, some of the temperature will be Kelvin. Despite the rant I had last week that said Kelvin, 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 saturated steam tables in temperature are presented in Celsius because it's easier to get your head around 100 degrees is where atmospheric pressure water boils. Right next to it, it has the saturation or sat temperature with a symbol T sat and a unit degrees C, and then it's got a series of data. It goes specific volume, internal energy, internal energy, enthalpy. Now we haven't defined enthalpy yet, and we certainly haven't defined entropy, but it has them. So just because we haven't defined them doesn't mean they don't exist. They're in the tables. It's a kind of a hint that we will go there. It gives everyone a unit. So specific volume, it will have the sat liquid, the sat vapor, and we'll give it a little symbol, VF, VG. Okay, or nu F and nu G, the little Greek lowercase v-shaped symbol. This guy will have sat liquid. It will have evap. And I'll talk about each of these terms in just a second. And then sat vapor. And we'll give a little symbol. Internal energy gets a symbol U. Not sure why. UF, UFG, and UG. Here the F means fluid, the G means gas. FG means the bit in between. Same pattern for enthalpy and entropy, so I'm not going to write them down, except that this would be H and this would be S, the symbols for enthalpy and entropy. It gives you units. So the units here, meters 3 per kilogram. The units here are kilojoules per kilogram, which is to say it is specific internal energy, not total internal energy. This is per unit kilogram. And this guy is kilojoules per kilogram. And this guy is kilojoules per kilogram Kelvin. So it gives you everything you need. It tells you what units, it tells you what terms, it tells you what symbols. In case you forget what a U is, you go, I don't even know what a U is, and you look it up on the table and, oh, okay, U is internal energy, that's great. So all the hints and tips are there, and they're in front of you. And then there's the numbers. This is a table this long, which is broken into 2 pages, and then there's another version of it, and then there's 18 tables, and you have to know which one to go to get the data and how to move around, and then you want a process which is going to take you from somewhere on the table to somewhere else on the table. So we're going to get good at moving around on tables, and we're going to get good at interpolation, which is the world's most boring maths, but if you get it wrong, you get your answer wrong. So don't make mistakes on interpolation. I tell you that I'm boiling at 2 atmospheres. My table is in kilopascals, and so it's got 100. It's kindly put in a line for atmospheric. 2 atmospheres is around about double atmospheric, and so there's other entries, and then it's got 200. And so you say, okay, well that's close enough for my purpose. It's not exactly 202.6, but it'll do for now. And then it's got a series of data. The first thing it tells you is at what temperature would I boil. If I'm boiling at a certain temperature, and it's a 120.21. Please note the decimal places. I don't want you to memorize decimal places. The decimal places used in the table are a good guide as to how precise to write your answer. So if you calculate, it tells you 17 decimal places. The tables are written with 4 significant figures. Provide your answer with 4 significant figures, or 3 decimal places and a number out the front. So if the temperature here is written with 5 significant figures, don't give me an answer after calculation that has 17 significant figures. You did not have the data to enable you to write an answer with that precision. I can come back to that point if anyone ever wants to talk about this. This guy and this guy, these are the values when I cross this line on the F side and when I cross this line on the G side, on the fluid side and the gas side. So the specific volume is when I'm fully a liquid, that's my specific volume, and when I'm fully finished boiling, that's my specific volume. So it's here and here. And somewhere in between is somewhat boiled, on my way to being fully boiled. Likewise, UF, UG, everything. I get my fluid value and my gas value. So if I tell you I'm in the process of boiling, I'm at 2 atmosphere, therefore I'm at 200 kilopascals. If I said, what's the temperature? You just look it up. It is that easy, there's no extra trick. Then I said, I'm 50% boiled. What's my specific volume? My specific volume is halfway between this number and this number. So that's, the very last slide is about the maths of this X, the X, which is a percentage boiled, or it's called the quality. So at this point, if I just say I'm boiling at 2 atmosphere, I haven't told you enough information to know the state. The moment that I said I am 50% boiled, I've now pinned down the state. I've given you 2 independent intensive properties. The percentage boiled is a property of the state. So if I said I am a saturated liquid, that's a code word. If I said I'm a saturated liquid, that's a code word for I'm 0% boiled. If I say I'm a saturated gas or a saturated vapor, that's a code word for I'm 100% boiled. These are little tricks. The question, you look at the question and go, I don't have enough information to solve it. You always have enough information to solve it. It's just you haven't learned the code words yet. We don't give you, at Intro Thermo, we don't give you problems that can't be solved. We do give you problems that test how you're going with the code words. So if you're sitting there going, I'm stuck, it's not because the info's not there. It's because you either haven't yet got your head around all the code words, or you haven't been able to work out how to jump your way around the properties. And that's the point of the exercise, is to test whether or not you've got there yet. So these will have crazy numbers in them. And I'm going to write down just a set of numbers to keep us going. 0.001061 and 0.88578. 5 significant figures, 4 or 5 significant figures. About 1,000-fold increase in my specific volume. The process of taking a liquid and turning it into a gas, in the case of water, is about 1,000-fold increase in the volume it occupies. And you can see that in the specific volume, it goes from 0.001 to almost 1. At this pressure, it's not fully 1,000-fold. At atmospheric, it's pretty close to 1,000-fold. So likewise, the density has gone down by 1,000-fold, because that's just the inverse of density. The saturated liquid has a certain amount of energy, and the saturated vapor has a certain amount of energy. And so these are the tables for all of that. So if for some reason you've been working your way through your problem, and you knew the energy that was contained by my fluid, and it was between these two numbers, so just for the sake of having numbers up here, this would have been 504.50. This guy would have been 2529.1. I know you can't read that from right up at the back, except that there are numbers on the board. There's a column in the middle, which is the difference between this and this. It's just there to save you one more line of calculation. Sometimes you need, if I want to work out what the value is halfway along, I need half of the difference added on to the original number. Okay, if it's 50%, I could have just averaged the numbers, right? But imagine it was 53.7% along the boiling process. So they also tabulate the difference between these two just to save you one step. As you get more and more into it, you'll realize it's nice to have that written down. But you want to make sure the tricky thing here is now, I've got rows of data at about, depending on the table, it might be at 5 or 10 or 20 degree intervals, going off to whatever temperature. I've now got loads of columns of numbers as well, and that's just one table, and I've got plenty of tables to play with. It's a tricky exercise. You think, well, can I just look this stuff up? Can I just type it in somewhere? In the end, as a professional engineer, yes, you can. Of course, all this data exists. It's verifiable. It can be put into a program. If you haven't played around with this kind of stuff, you don't know where the numbers are coming from, you don't know how they connect to each other, and you don't know how the processes moved between them. This is why we still teach property tables, and it's why every single thermo textbook still has property tables in them. Is because the exercise of playing with the tables gets the idea, gets the skill set into you much, much deeper than having something just handle it for you. You don't even know what it's handling until you've done this, and then you go, thank God I don't have to do that anymore. But if it was already doing it, then you haven't built up any thermodynamic skill, any thermodynamic depth of understanding of the processes. Okay, imagine this data set exists in this table. This is the temperature saturated steam table. And instead of press and saturation temperature, it goes temp and saturation pressure. And here I've got 120 and I've got 130, for example. And I said, I'm boiling at 120.21. I've got a row of data here and a row of data here. This guy might say, if that was 200, this guy might say 198, and this guy might say, let's say 257 kilopascals. And I say, I'm boiling at 120.21 degrees. You come to this table. What pressure am I boiling at? Don't know yet. I have to interpolate between these two values to work it out. Okay, so at some points there's just tedious interpolation to be done, but it's accurate, and it's part of this subject, so you have to. But the point I was making before is this data, these data, and these data are identical. They're tabulated at different breakpoints, but they are self-consistent to within the necessary accuracy. Now I say that because if you actually do the exercise of taking this value and putting it in here, you might be off by one decimal, a decimal place. But the rounding is sufficient that these are self-consistent. So if you find yourself on the wrong table, that's not a disaster. The wrong table. I shouldn't say the wrong table. If you find yourself on the other table, it's not a disaster, but you choose the table that makes your life the easiest. Hooray, I'm talking about tables to people in the classroom. I say that this is not something that really should be sketched out. However, I'm also finding that the process of writing it on the board and yelling out different parts is more useful than flashing up the screen and having you not read it, because it's a lot of compact, detailed information. If it just goes up on the screen, you also don't see it. So this to me is a teaching luxury that I get to scribble and yell. Okay. I have this boiling liquid, I have this boiling steam, and I'm done boiling. And I shoot off the edge of the table. I tell you, I'm steam at 2 atmospheres, and my temperature is 121 degrees. I come to this table, I go, okay, I want to look up my properties. I come to this table and I go 200, so 2 atmosphere. So I tell you I'm boiling at 200 kilopascals. I come to here and I told you that my steam is at 121 degrees. And I see this number, and I go, well, maybe, just maybe, I could still use the table, because it's only 0.79 degrees off. No. No, no. To this precision, the temperature and the pressure are not independent, they are connected. If you are off this precision, you're either fully liquid or fully steam, fully vapor. So at 100, the moment that I go to 120.22, I'm fully vapor. So to this precision, that is accurate. So if I told you I'm 120.22, I am no longer on this table. I no longer can look up this value or this value to tell me my properties. I then have to go to the superheated tables. And superheated tables, there's many more of them, because these guys have the nice benefit of temperature and pressure always being connected, and I'm just trying to interpolate between 0% and 100% boiled. Superheated have to map the whole possible combinations of temperature and pressure, and then let me look up specific volume, internal energy, enthalpy, and entropy. So I will draw up one tiny subset of a superheated table and let your minds imagine that there are others. I'll do it over here. Actually, there's a good spot. There's a great spot. Saturated water temperature, saturated water pressure, superheated. Almost there. You guys are doing a great job. Thank you. So, superheated, steam, comes in chunks. So it'll have one box here. Down here will be temperature, for example. And it'll have one box here for pressure 1, one box here for pressure 2, one box here for pressure 3, and then rinse and repeat, more temperatures. So this temperature will come down here, and then temperature will come down here. This guy will be pressure 4, pressure 5, pressure 6. Yep. So this might go from, let's say, it might go from 50 degrees to 1300 degrees. Yeah? And it might go 100, 150, 200, 300, 400, 500. And inside the pressure box will be a column for V, U, H, and S with the units. The first thing I'll list is Psat equals, let's say this was 0.01 megapascals. It'll have Psat, and the first thing that gets listed is the saturation, not Psat, Tsat, sorry. The first thing that gets listed is the saturation properties, and then the first temperature. So here it will say 45.81 degrees C. Here it will list the saturation properties. The values in this column, in this row, are these values: the VG, the UG, the HG, the SG values. So they're the point at which I jump off the saturated tables and go on to the superheat tables. So that's the first bit here. And it just says SAT because it's already told you what the temperature is at SAT, and it just saves them having to write out specifically on every table the saturation temperature. And then it goes 50, 100, 200, 300, 400, 500. And so if I say my pressure is 10 kilopascals, so partial vacuum, and my temperature is 100 degrees Celsius, tell me my specific volume. You go, okay, I'm on this table. I come to the row for 100, and I look up specific volume. So far, so good. So far, so easy. Then I say, I'm going to increase the pressure from this to 100, to atmospheric, to 100 kilopascals. Then I go across, and maybe this one is 100, maybe this was 50 kilopascals, or 0.5, and then maybe this is 0.1, 0.05 and 0.1. I say, well, now at that extra pressure, I've got a different specific volume. So I'm looking at my properties on a property table for superheated steam, because I no longer am on the saturated tables. The question won't always tell you whether you're saturated or not. So you have to be able to go, at the beginning of the exam question, you have to be able to say, what table am I on? First, what fluid is it? It's steam. Okay, I'm on the steam tables, so don't pick up an air table, don't pick up an ammonia table, don't pick up a refrigerant table. Second, am I saturated or superheated? Don't know yet. Let's see what I've got. If I've got temperature and pressure, that should be easy. I can just jump on here and check the numbers. If I had pressure and specific volume, for whatever reason, maybe I got told the mass and the volume and I could work out specific volume. So I had pressure and specific volume. If I'm in between these numbers, I'm on this table. If I'm bigger than this number, I'm off the table, onto the superheat tables. So the first thing you're doing is working out which table to pick up. You've got all the tables available. Imagine you're in the exam. You're shuffling, shuffling, shuffling. Which table? Okay, superheat tables, good. Now I'm on a superheat table. I find which pressure or which temperature or which combo, and then try to work out the rest of my properties. You don't always have temperature and pressure. Sometimes you can have any two independent properties. So you might have entropy and pressure. You might have temperature and internal energy. Any of those pairs can pin you down. Yep.
Can you please repeat which table, how to choose the table?
How to choose the tables. Yes, I can repeat that many times, and I will. Good. I'm glad you're asking me to repeat it because I don't want you to miss this one. I'm on the saturated tables if I'm in the process of boiling. So, if I'm in the process of boiling, my temperature and pressure are fixed until I'm finished boiling. So imagine I tell you my pressure, I haven't told you my temperature yet. I tell you my pressure is 200 kilopascals. And I tell you my specific volume is 0.5 cubic meters per kilogram. You go, okay, 0.5, 0.5. Step one, let's pick up a saturated table. 200, 0.5, 0.5, 0.5, specific volume. I find my specific volume lines. 0.5 is between these two numbers. That's cool. I'm still in the process of boiling. Okay, so this is the right table. I tell you I'm at 200 kilopascals, and I tell you my specific volume is 1.0, you go, okay, I don't know where I am yet. You have to begin somewhere. Pick up a table. Pick up the saturated table. It's easiest, I find, to start with a saturated table because it's just one table. Well, two, but it's not all the different tables to go hunting. 200 kilopascals, and I tell you my specific volume is 1.0. I come over here, and I go, but hang on. 1.0 isn't between these numbers. It's bigger than this guy. It's bigger than my vapor, my saturated vapor specific volume. So I'm off this table. So when you come to a number that exceeds the vapor number, you're off the table. The other game that I suggested is possible is if I gave you temperature and pressure, if I gave you 200 kilopascals and 120.21 degrees Celsius, you look this up and you go, sweet, I'm on this table. If I gave you 200 kilopascals and 120.20, I'm off this table, I'm a liquid. If I gave you 200 kilopascals and 120.22, I'm off this table, I'm fully boiled. So the temperature-pressure combo is exact to within the precision of the table. So I give myself a few minutes to talk about interpolation because I want you to follow some rules. You can see, by the fact there's all this data, you can see there will be times where you need to find the values in between the rows or in between the columns. So you need to interpolate. I will put it here. Interpolation is from the value that I started how quick can I do an interpolation? If you've never seen one before, I'd be surprised. I got x1, x2, y1, y2. I've got some graph where I know this point and I know this point. I know that if I were at x1, I'd have y1. If I were at x2, I'd have y2. And I say, what about if I had just x? What would be my y? If I had the perfect graph, I wouldn't need to interpolate. I would just look it up. Yeah? If I had the curve, I could just look it up. If I'm interpolating, if I'm doing linear interpolation, I assume it's a line between the 2 points. I have enough information from these guys to work out the gradient of that line. And then I'm stepping along from this value, I'm stepping up the gradient to here. And I'm a little bit off the truth, but close enough that it's okay. I don't let you interpolate in thermo if it will result in an imprecision that's not acceptable. How do I know? The rows are written with gaps that are interpolatable. You don't interpolate over 5 rows. You interpolate between 2 entries. That's okay. Interpolating over 5 rows is not. Extrapolating, which is going beyond my x2, is not okay. Interpolation in this circumstance with these tables is fine. The imprecision is fine. The equation, I mean, you can write this any way you want. X minus x 1 over x2 minus x1. And try to get this all done in the next 2 minutes. I can do this. y2 minus y1. I'm just going to talk this through in words, plus y1. My new y, my new value y, has to start from my old value y and add a bit. So here it starts from my old value y and it adds a bit of the difference. How much does it add? It adds the percent of the way that I am along this line. Okay? If you rewrite that, you end up with the equation of a line, right? So imagine this is halfway. I'm 50% of the distance between x1 and x2. So that would have been x minus x1 over x2 minus x1. This would have been 50% or 0.5. Imagine y2 and y1 were 2 and 1, okay, of 2 minus 1 plus y1, because I can't just add 0.5. I have to add, I can't just say the answer is 0.5. It's not. The answer is 1.5 because I'm halfway between 1 and 2. So plus y1. This gives me 0.5. My answer